So today we're going to be doing the right half of page 4 of the Semester 2 Review Guide for Algebra 2. So let's take a look at starting at number 34. So we're going to zoom in at number 34. Okay, so we're asking for what is the inverse of the following function. So I have this function f of x is equal to x plus 4 squared minus 9. And I want to find the inverse of that function. Now, if you remember, the inverse of the function does one of two things. I would like to write this as a y equals x plus 4 squared minus 9. We can either solve for the other variable, meaning I can solve for x in terms of y, or I can rewrite this as put my y in this place and my x in this place and resolve for y. One of the ways that I like doing this is I like going ahead and just solve for x because it highlights that we're looking at this from another perspective. The same relationship from a different perspective. So this is asking what is the inverse specifically. We'll come back on that here in just a moment. So if I want to find the inverse of this, I'm going to slowly isolate the x, which means I need to get rid of that minus 9. So I get y plus 9 is equal to x plus 4 squared. The next thing I'll need to do is I'll need to take the square root of both sides. Now, please keep in mind that when you artificially introduce a square root like this, y plus 9 is x plus 4, is I need to do both the positive and negative of this square root. So I get both of these. If the square root already existed, it will have either a positive or negative, but if I artificially introduce it, I have to take both. Last thing is I'm going to subtract that 4. So I have the positive and the negative. Y plus 9 minus 4 is equal to x. So now this is the inverse of this function. I like writing it like this. However, many swap the x and the y for the way you write it. You can write this as a y equals positive or negative, x plus 9 all rooted, minus 4. And this is depending on the script of your answer. Again, I like solving it like this because it highlights that we're looking at the same relationship as original from a different perspective, but you can also rewrite it like this. The other thing that you may encounter is if it asks for an inverse function, is that a function? And the answer would be no, this is not a function, but it is an inverse equation, which is all the question asks for exactly. It doesn't ask for the inverse function, just ask what is the inverse. So the inverse is whichever way you would like to show your answer for this. Okay. So we're going to go ahead and we're going to do this again for number 35. Okay. So g of x is equal to root x minus 6 plus 5. Again, this is just asking for the inverse. It's not asking for the inverse function. So we know that even if I have something that would not be a function, we're okay to do the inverse. So our first step is to rewrite it as a y value, x minus 6 plus 5. And I'm going to slowly work my way into and solve for this x, which means I'm going to subtract the 5. So y minus 5 equals root x minus 6. Next thing I have to do is get rid of the root, which means I'm going to square both sides. So y minus 5 squared, and if I square a square root, that disappears. The next thing is I'm going to add my 6, so y minus 5 squared plus 6 is equal to x. Again, I like to keep it like this simply because it highlights that we're looking at that same relationship as before, but from the other variable's perspective. However, the more common answer you might run into at this point is we rewrite it as y equals x minus 5 squared plus 6. So again, however the script necessitates, I tend to write it like this. However, you will get some answers that say, hey, actually do go ahead and swap the x and y. Perfect. So let's put a line through that and knock into number 36. So number 36 says, given the coordinates negative 5, 6 lies on the function h of x, what point must lie on the inverse of h negative 1 of x? So the h negative 1 is the inverse of h. And remember, the inverse simply means, as we've done previously, is we've swapped the x and the y's. So if this lies on h, what point must lie on the inverse? Well, let's swap the x and the y's. It's just going to be 6, negative 5. That's it. (37). Let's take a look at the next one. Determine if the following functions are an example of exponential growth or decay. So this is actually a multi-part question. I have A, B, C, D, and E. So let's go ahead and copy these down. So for A, I have that. For B, C, D, E, and E. Okay, so we're looking for exponential growth or decay, which highlights one thing that we're looking for. The first number in each of these functions is the starting value. So what I'm looking at here is where the function starts. So this is my starting point. The next number, which is the base of this power, is going to be either my growth or my decay factor. So all of these are what I want to pay attention to. Let's take a look at this. So if these are my growth or decay factor, this is the important part of the question. Hold on, let's zoom out just a bit so we can look at them all at once. So if I have my growth or decay factor, now this question is worded in a slightly awkward way because with the negative 4, this is going to be behaving in a flip direction as opposed to a positive number. So if I'm starting at a negative, I'm going to move in a weird way. So growth or decay factor explicitly states if this value, if the growth value is greater than 1, it is growth. Plain and simple. If that growth value is between 0 and 1, then it is decay. The idea is that if it's between 0 and 1 and I multiply by a number between 0 and 1, let's say it's half. Well, if I have a value of 1, half of that is half of that is a quarter, half of that is an eighth. I get smaller and smaller and smaller, hence decay. If the value is larger than 1, let's say 2, and I start with 1, 1 times 2 is 2, 2 times 2 is 4, 8, I'm getting growth. My numbers are getting bigger. So explicitly stating, for A, that 1.8 is going to be growth. For B, that number is between 0 and 1. I'm multiplying, I'm going to slowly get smaller and smaller and smaller. This is decay. 5/4 is larger than 1. I'm going to get growth. 3 is also larger than 1. I'm going to get growth. This is smaller than 1. 4/7 is not quite 1, so this is going to be decay. The slightly awkward part of this question is the shape of the graphs don't necessarily dictate growth or decay. Growth or decay simply say, is the number going towards 0 or moving away from 0? Growth means the number is getting bigger, it's moving away from 0. Decay, it's getting smaller, it's moving towards 0. If we look at the shape of this graph, the shape of 0.9 raised or times 1.8, the number starts small and it gets bigger. That very much looks like the growth that we said it was. However, this -4, we know it's decay, it's moving closer to 0, but that -4 is a value that does this. That looks like it's getting bigger, but remember, our function if I were to draw the x-axis, it's getting closer and closer to 0. This function's moving away from 0. This 0.3, this number is getting bigger. Again, it's moving away from 0. It's moving away from my 0 line. The negative 2.6 is moving away from the 0 line. However, because it's negative, the way to move away from the 0 line looks like it's going down. But again, it's moving away, so it does classify as growth, but it's a negative growth. And then this one, 5 and 4/7, because it is decay, it's moving towards my 0 line. So that does look like decay, and it is decay. The only things that don't necessarily look like the way they're classified is if I have a negative value. This is decay, even though it's increasing. This is growth, even though it's decreasing, because it's moving either towards or away from that 0 line. The value or the volume of the number is either getting bigger or smaller. And that's what necessitates growth versus decay. Okay. So that is number 37. Number 38, we're going to move on to a sheet of graph paper. Let's put a pause in that regular sheet. Let's pop over to number 38. Okay. 38 says graph y equals 2 to the x. Okay. And we want to state the domain, the range, and the asymptote. So we need domain, I need range, I need asymptote. Okay. So first off, when we look at this, what we've just covered is a few of the values. I have 2 raised to the power of x, which means that this graph is going to be getting larger and larger. Because it is a positive value out here, you don't see the starting point because I don't see the set of parentheses surrounding the 2. I don't see the 1 written out, but I know it's a positive number increasing. So if I were to graph this, let's see. This one's a hard scale, so 5, 4, 3, 2, 1, 0. We go all the way down to -1, -2. So I can't scale this according to my own standards. The graph that they gave us has these values listed on it. So what I could do is I could do one of 2 different things. I could either say, hey, let me make an XY table, plug in values and see what I get, or I could recognize some basic relationships here. Okay. Well, I could plug in some numbers and say, okay, well, let's start with 0. Let's see. 2 to the 0th power is 1. I could plug in a 1. 2 to the first power is 2. I could plug in a 2. 2 squared is 4. 3. 2 to the third power is 8. I could plug in a -1 and try and work this algebraically. Or what I could notice is when I plug in my starting point of 0, I should always get a value of 1. I should get that starting value right here, 1. What am I doing to that number? Well, as I move to the right, I'm multiplying by 2. So what is 1 times 2? 2. What is 2 times 2? 4. Which is why I get the points 1, 2, and 2, 4 on my graph. I would have 3, 8 because 4 doubled is 8, but I don't need that. Now if I'm doubling going in this direction, I'm going to cut in half going in the leftward direction. So half of 1 is a half, half of a half is a fourth, half of a fourth is an eighth, half of an eighth is a 16th. And it's going to slowly get closer and closer to this. So again, I could just look at this and understand intuitively what's going on, or I could actually work this out algebraically and say, well, what is -1? Well, 2 to the -1 is equal to 1 over 2 to the first, which is 1/2. Gives me that point. I could plug in a -2 and say, well, 2 to the -2 is 1 over 2 squared, which is 1 over 4, and it'll give me that point. Or I could just notice that I'm multiplying by 2 as I go to the right and dividing by 2 as I go to the left. The other thing this asks for is it asks for an asymptote. Now, with exponential functions like this, we notice that it starts to flatten out. and it flattens out right here at the axis. And this says it's going to try and get closer and closer to 0, but it'll never actually get there. So as far as our asymptote, we know that y will not equal 0. That gives us everything we need to look at the range. So our range, all y values, well, if it never equals 0, it won't go on the other side. So my range is going to be all values above 0. So 0 all the way up to infinity. And because I can't reach 0, I don't include 0. The domain is all possible x values that I plug in, which goes infinitely to the left and to the right. So I could either put all real numbers, or I could put negative infinity to positive infinity. Boom. There we go. Domain, range, and asymptote. So taking what we know on number 38, let's try number 39. And so what we're going to do is we're going to use that intuitive approach for how the graph moves. Now number 39 is not an exponential. It is the inverse of an exponential function. It is a logarithm. So y equals the logarithm of 2 to the x. And we want to say domain, range, and asymptote. So let's get that written down. So first off, we know that with a logarithm, let's go ahead and double check, make sure I've got the right scale on here. Again, this is a hard scale. The graph that they give you is going to be scaled exactly like this. So 1, 2, 3, 4, and 5, -1, -2, 1, 2, 3, 4. Okay, so it must fit in this grid, no more, no less. We know that the logarithm is the inverse of an exponential. If I rewrite this logarithm as an exponential function, I know it's going to be 2 to the power of y equals x. So 2 to the power of y equals x, which is very similar to our previous function. It literally is just swapped with the x and the y. That is why a logarithm is the inverse of an exponential. So I can actually take my table from number 38 and swap it around. If we didn't have a direct relationship between these two, all we would do is we would set up this relationship, but instead of plugging in x's, I would plug in y's. So let's assume that we don't know that number 38 is the same thing. I would just go ahead and set up an x and a y. And I would treat this like an exponential and say, oh, okay, it's 2 raised to some power. So why don't I plug in my 0? And again, instead of plugging in a 0 for the x, I'm going to plug in a 0 for the y and say anything to the 0th power is 1. Now, I'm going to move with my y's and say, okay, or I'm going to move around my x's instead of around my y's and say, well, this doubled, 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 halved, halved, halved. I'm going to move my x's. Well, for my x's, moving up, it's going to double, 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 halved, halved, halved. 1, 2, 3, -1, -2, -3. Perfect. Again, it's the same type of relationship, just swapped. Okay, so what does that look like? Well, if it's the inverse of this, I should expect this to be reflected across that line. I should see a line that looks something like over here in these two quadrants. So let's take a peek at what that looks like. Okay, so if x equals 1, y equals 0. And as I move up on the y, I'm doubling my x. So if I move up, I double. If I move up, I double. If I move up, I'd be way over here at 8. And as I move down, I half. So as I move down 1, I cut it in half. Down 1, I cut it in half. So I see something just like what we expected that does something like that. Now again, if a logarithm is the inverse of an exponential, and exponentials all have an asymptote that is horizontal, the inverse of a horizontal line is a vertical line, which means that we'll notice that my graph is slowly approaching 0 on the x-axis, but it won't actually get there. So x can't equal 0. It's going to try to, but it's not going to make it. my asymptote for this is going to be x can't equal 0. It really, really, really tries, but it never will. My range this time, I've just swapped my two values for these. So my range, how far up or down does the graph go? Well, the range is all real numbers, or from negative infinity to positive infinity, however you want to write that. This time my domain is limited. If it can't get to 0, it won't get to a negative value. So I'm going to have to include only the positive values, so from 0 to infinity. And I won't actually include 0, so I'm going to put a parenthesis. And there we go. So we graphed our logarithm. Okay. So at this point, number 40, we can kind of flip back to our original sheets of paper because we're no longer needing to graph these. Let's pop this down for number 40. Okay. Given the parent function of this, describe the transformation. So I have to describe what happened from this function to this function. Okay. So if I have the original function f of x equals the base of 5 raised to the x power, and I have my new function of negative 5 raised to the x minus 2 power. So with this one, we want to pay attention to when we have a power and I don't see a set of parentheses, I'm assuming that the negative is not included in the set of parentheses. That's just a general assumption we're going to make. So I want to describe what happened from here to here. Well, a couple things I need to take note of. I did change from a positive to a negative, which means the graph must have been flipped vertically. So I have a vertical reflection. I misspelled that. It's reflection. A little bit of dyslexia there. Vertical reflection, or what you could call a flip. So from positive to negative, the graph went from curving up to now it's curving down. The next thing I noticed is I went from an x to an x minus 2, which means the graph has been moved to the right by 2 units. So I have a vertical reflection or a flip, and then a rightward motion of 2. Okay. So number 41, we have a very similar setup. We have the parent function f of x is equal to 5 raised to the x power, and my g of x is equal to 5x plus 4 minus 1. Okay? So I want to describe what happened from this function to this function. Well, I'm noticing that my plus 4 is in the power, which means that is going to be a leftward motion by 4. I also notice I'm now subtracting 1 outside of the power, so I'm moving the graph down by 1. And there we go.